Hello. In this video lecture, I will be covering Chapter 11, Module 11. The subject of the chapter is elasticity and periodic motion. This semester, we're not going to be covering elasticity, only periodic motion. In other words, section 11.1 will be skipped, and we'll jump to section 11.2. It is on page 329, right here, periodic motion. What is periodic motion? When we say periodic, it means something that repeats itself over and over and over again. For example, the pendulum, a swinging pendulum in the grandfather clock, where it is click, 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 click. It's always moving to and fro, and the motion is constantly being repeated. Another example is, say, a mass attached to a spring, and it is oscillating up and down. That's another example of periodic motion. Even the motion of the Earth around the sun, every 365.25 days, the motion repeats itself over and over again. Or the spinning of the Earth around its own axis. This is also an example of, night, day, and so on. So this is also an example of a periodic motion or an oscillatory motion. Okay, so that's basically the topic that we will be covering. So what is a periodic motion in that sense? Periodic motion always has a stable or an equilibrium position that is always oscillating about. Let me explain that. Take, for example, let me just write down the topic. Periodic motion. Take, for example, the oscillation of a mass attached to a spring, for example. So here is the mass, and let's assume it is sitting on the floor. We are ignoring the frictional effects, and here is the spring, and let's say this is a wall or something like that, and then the mass is oscillating to and fro like this. Okay, so it is to the right and then to the left and to the right and to the left. We can say that if we assume that this is the equilibrium position, let's call it x equals 0, and the mass is oscillating from the right to the left like this. Here it is. Okay, so the mass goes all the way up to some value x here, and then back to another value of minus x. Okay, so here we have, this is the equilibrium position right here. Okay, and it is moving towards the x value here, and then back to the negative value. Okay, the reason for that is that when moved away from its release position, let's say the mass is starting at the release position of x equals 0, and let's say I pull it all the way to x and then I'll let go. So what's going to happen? It's going to rebound, or it will move toward the equilibrium position, but by the time it gets to the equilibrium position, it has already picked up enough kinetic energy to overshoot and goes all the way to minus x. Okay, of course in this case it has already compressed the spring, so it will rebound and goes back to the original position, which is the equilibrium, but again it has already picked up kinetic energy, so it will overshoot to the value of x and so on. Okay, so what's causing it to move is a force that keeps moving it towards x and then toward negative x. We call it a restoring force. Okay, and this cycle repeats over and over, and in this kind of motion we call it the periodic motion. Okay, so we can say that there is a force that is acting on the object, that tends to always restore it to the equilibrium position. In other words, see, if the mass, for example, is moving to the left toward negative x, while it's moving there, the force is going to be, because this force is a restoring force, once it brings it back to the equilibrium position, that force is always opposing the displacement x. You see what I'm saying? In other words, if I take this, let me draw it again. Let's say here is the equilibrium position, okay? And let's say the mass is moving in this direction, okay? So the displacement is in this direction. That's the direction of the displacement. Remember, displacement is a vector. So the displacement is moving to the left, but this restoring force is always opposing to it, and it is directed toward the right to bring it back to the equilibrium position. Now, when the mass here, and let's say it's moving to the right like that, the restoring force is now acting to the left, trying to bring it back to the equilibrium position. Okay, so in other words, the force here, this restoring force, is always opposite in direction with the displacement. You get that? And this force, we refer to it as the restoring force, is equal to minus kx. X here is the displacement or the elongation of the spring, okay? And k here is a constant. We call it the spring constant. And the minus sign here indicates that the force and the displacement are always directed in opposite directions. So the minus sign here indicates they are in opposite direction. They're not in the same direction. If it's in the same direction, eventually the object is going to stop. It's not going to oscillate. So the purpose of the oscillation, really, or the periodic motion, is this negative sign, is that the displacement and the force are always in opposite directions. Okay, and k here, like I said, is called the spring constant. Okay, I like to call it the stiffness constant. The stiffness constant. Stiffness, basically the k value here tells you how stiff the spring is. The larger the value of k, the stiffer the spring. You got that? And if you look at the unit of that thing, so if you take that formula and solve for k, so that will be f over x. I'm ignoring the minus sign for now. If you just look at the scalar value of it, so the unit of this thing would be Newton per meter. Okay, so that's the unit of the stiffness constant. Okay, more on that in a minute. Okay, in addition to that, since this force is a dynamical force, and we know that from Newton's second law, F equals ma, and this force also equal to kx. Again, I'm ignoring the minus sign for now. We're just looking at the scalar value. Notice that the acceleration in this case is going to be equal to k over m times x. What you notice here is that the acceleration in this case is a function of position. In other words, as you increase the position or the displacement, as the displacement increases, the acceleration actually increases. And the converse is also true, which means what? That the acceleration here is not constant. Okay, this is important. So in the periodic motion, the acceleration is not constant because it is a function of position. Okay, again, more on that later when we start doing problems, examples. Okay, just a little bit more. So let me go back to that oscillating mass again. So let's assume that this is the equilibrium position of the mass right here. And we said that it is moving back and forth like that. And let's assume that the mass mass is the maximum displacement is right here, and we called it x, and this is the maximum displacement on the other side. Let's say right here, and this is x equal, sorry, it's just minus x, right? It's just minus x, okay? This maximum displacement, we call it the amplitude, and it has a symbol A. And of course here it is minus A, okay? So A here is the amplitude. The word amplitude in physics basically means the maximum displacement, okay? Always. So, in other words, I mean, the mass could be at some position, say, right here, at some x value, you know, whatever it is, x, we'll call it x1, for example. And that, of course, is not the amplitude. It's just some displacement, and we measure that displacement from the equilibrium position to that value, okay? So that will be the displacement of the spring right there. But specifically the maximum displacement, which is basically the maximum distance the mass or the block reaches before it returns back, is called the amplitude, okay? So the amplitude is a word for maximum displacement. This is important. Maximum displacement. Okay? So notice that, again, I'm going to draw it one more time. So here is the equilibrium position right here, and here is the maximum displacement right there. Notice that the amplitude here, which is the maximum displacement. So here we have a cycle. It goes from A to 0 to minus A. Do you see that? Let's say we take, let's assume that we run the film starting where the mass is here. So what's going to happen to it? It's going to return back, and it's going to pass through the equilibrium position, and it's going to go all the way to minus A. And then what? It's going to start, and then it's going to stop, right? Because this is the maximum displacement. And then it's going to return, rebound, and it's going to go and passes through the equilibrium and then back to where it started, the position A, okay? So that would be one cycle, and then from minus A to 0 to A, okay? We call that one cycle. You got that? Now, the time it takes the mass to complete one cycle, which means let's say it's starting from A, so it's going to go through x equals 0, all the way to minus A, and then back to x equals 0, and then to x equals A. This is called one cycle. Okay, the time it takes to complete one cycle, the time it takes to complete one cycle is called the period. Okay? It's called the period. So that's the time. Remember, a period is a time. The time it takes to complete one cycle. And the symbol for period, your book uses capital T. I don't want to use T because later on we may cover, the thermodynamics, and that will be for temperature. I like to use the Greek letter tau. Okay? Again, we also used it for torque, but we're not going to be doing torque in this chapter. So tau for period, okay? We also have another one, is the number of cycles per second. Number of cycles per second. In other words, imagine that that this mass is oscillating back and forth like that really fast. So fast you can't even see it, let's say, okay? So it is making maybe 5-6 cycles per second. You see what I'm saying? You know what I mean? Those number of cycles per second, we call it the frequency, okay? Per second is called the frequency. Okay. And the frequency, the symbol for it is small letter f. And period and frequency are related by this simple relationship, is that the period is the reciprocal of the frequency, and the frequency is the reciprocal of the period. Okay. Now you can imagine the unit of the period is second, and the unit of the frequency, as you can see in this equation right here, is 1/2, correct? And we refer to this 1/2 as the hertz, Hz. Got it? Hertz. Okay. Let me show you an example of how all of that can be applied. Let me start with a simple one. When I find it, example 11.4 from the book. Here are the formula that we are dealing with. Oh, and I forgot to mention omega. I'll come back to it in a sec. There we go. It says here, let me get it bigger. There we go. It says in this example, we will look at the periodic motion of an ultrasonic transducer, a kind of ultrasonic loudspeaker used for medical diagnosis. This is it here. The transducer is oscillating at a frequency of 6.7 megahertz. Okay, so what does that mean? It means 6.7 mega is a million, so that means this device is oscillating or making cycles 6.7 million cycles per second. You got that? That's the meaning of it. It's really, really, really fast, right? So it's 6.7 million cycles per second. Now he's asking how much time does each cycle take and what is the angular frequency? All right, simple problem. So he said that the frequency of this device is 6.7 megahertz. Remember, the mega is 10 to the 6 is a million, right? A mega. And now he's asking for the period. We're going to call it tau. And he's asking for angular frequency. I'll come back to it, but it's basically omega. Okay? So we know that the period tau is 1/f. So all I need to do is just 1/6.7 times 10 to the to the positive 6, because that's a million. And then when we use the calculator for that, you will end up getting 1.5 times 10 to the -7 second. Really tiny amount, okay? Now I can write it in terms of microseconds, so that will be 0.15 microsecond. A micro is a millionth of a second. Microsecond, a millionth. Which is basically opposite of the mega. Mega is 10 to the 6. Micro is 10 to the -6. Okay, here's a good abbreviation that I would highly advise you to memorize. Okay, and then he's asking for what is the angular frequency. We talked about omega, if you remember from previous chapter, and we call it the angular velocity. They're pretty much the same. They also have the same unit. Okay. But when it comes to periodic motion, we use the term angular frequency. It's just, like I said, it's the same as angular velocity. So omega here is the angular frequency. That's just another name for it. Again, like I said, we can call it angular velocity, but it's angular frequency, and it is equal to 2 pi f. Okay? So omega is equal to 2 pi f. That's the formula for it. I hope you are taking notes and writing down all these formulas. There is a lot of little formulas that we're going to be using. So maybe you want to put them in one sheet, so when you are working in your homework, you have all those formula in one sheet. Of course, as you know, that since f is 1/tau, so I can also write the angular frequency as 2 pi over tau, whichever convenient for it. They're both equivalent to give you both the same answer. So now he's asking for what is omega. Angular frequency, we said, is 2 pi f. So I already got, it's given to us. The frequency is given to us. So we got 2 pi times f is given to us 6.7 times 10 to the 6. And then we just multiply that. 2 pi is 6.28. And when I calculate that, 6.7, and answer 4.2 times 10 to the 7. And what's the unit of omega, guys? Radian per second. Same unit, okay? What that means, it means that it's making this many radians every second, okay? Remember, a radian is just another unit that is analogous to degrees, okay? So it's making this many radians per second, okay? Okay, good. The next topic in periodic motion is energy. This is an important topic. The chapter is short. I hope I hope it's also simple. It's not very complicated like the previous one. I forgot to mention, there is another term that we use for periodic motion, and that is SHM, simple harmonic motion. So periodic motion if the force is equal to minus kx, okay, then the motion is, again, we said oscillatory motion, periodic motion, cyclical motion, or simple harmonic motion. Simple harmonic motion. I will explain what that means in a minute, what that means, and for abbreviation we just call it SHM, okay? So SHM means it's simple harmonic motion. Again, periodic motion or oscillatory motion, okay? And why we call it simple harmonic, I'll come back to this in a second. But that's just another name for it, okay? So the topic, section 11.3, energy in SHM, energy in simple harmonic motion. So what does that mean? All right. Let's go back to the drawing that I have done, the diagram that I've done with the oscillating mass. Remember that? So here is the floor, or maybe an air track or something like that. Here is the mass. Again, it is at the equilibrium position. And let's say it's oscillating to and fro. Let's make it a little bit farther. Again, there is a spring there, but we're going to make the spring invisible. Okay, but we are concerned about here the motion itself. So here we have the mass moving to and fro, if you will, and we said that these are the maximum displacement. We call them x equals the amplitude A, and this is x equals minus A, correct? Okay, and it's moving, right and left like that. Okay, now we know that the energy, the total energy, is equal to kinetic energy plus potential energy, correct? Now, for a spring, and I think we mentioned that in a previous chapter, for a spring, the potential energy is equal to 1/2 kx squared. Remember that? That's the potential energy. So the total energy in this case would be kinetic plus potential. Let me just write it down. Where the kinetic is 1/2 mv squared plus the potential 1/2 kx squared, right? That's the equation that we will be dealing with as far as a spring mass system is concerned. Got it? So the kinetic, which is basically it gives you the how much motion energy there is in the mass, in the oscillating mass, and then you have the potential energy. Now let's look at this diagram that I just, the one I just drawn here, and in light of the of energy. Now you agree with me that at the equilibrium position here, the spring is relaxed. It's not stretched, correct? Remember, the way the motion started is that we have the spring here, somewhere all the way to some, a wall or whatever. Here is the spring. The spring is relaxed, okay? And then what I do, I hold the mass and I pull it all the way to here, x equal a, and then I let go. So what's going to happen is going to go all the way here and then back and forth, back and forth, back and forth. See what I'm saying? That's basically what's happening. Okay, so before I pull the mass while it's here, there is no displacement in the spring. What that means, there is no potential energy in the spring. Make sense? Right here at x equals 0. So at x equals 0 here, the mass is at rest, if you will. Remember, before I pulled it. So here we have the kinetic is 0, and I'm sorry. What I'm trying to say is that when I pulled it, the x here is equal to 0, so that means the potential is equal to 0. Okay, I'll come back to the kinetic in a sec. All right. However, here, at the maximum, remember I took the mass, I held it in my hand, and I pulled it all the way here. Now I'm holding it. Before I let go, the kinetic is 0 because I'm holding it in my hand so that it's not moving. However, it has gained a lot of potential energy, spring potential energy. So here we will have, right there, you have a potential is equal to 1/2 k x squared, but specifically, this x is actually the maximum x, the amplitude. So it's equal to 1/2 k a squared. You see what I'm saying? Same thing as here. U here is 1/2 k a squared. It's minus a, but minus squared is become positive. So far, so good? Okay. Now, so let's say I'm holding the mass here, and then I'll let go. So what's going to happen? Well, it's going to go back this way, and while it is going back, the displacement is decreasing. This value of x is decreasing until it becomes 0 here. In other words, at this stage, remember, it's going and it's going to go all the way to x equal minus a. But right at this moment here, if I would stop the film from running, what's happening is that it has reached a maximum velocity here because all the potential energy has gone to 0 because the displacement is 0 here. And all that potential became 0 and converted into kinetic. Okay? So here, while U is 0, but you have the kinetic energy, K, is equal to 1/2 mv squared, where v here is actually a max. Make sense? Got it? Now, at any arbitrary position, let's say here, let's say here, for example, right here, some arbitrary position, not necessarily in the middle, somewhere here, okay? At this position, what is the total energy? Well, the total energy is basically 1/2 mv squared, whatever the velocity of this object here. Let's assume that the object is moving in this fashion, plus 1/2 k x squared. And x here basically is the distance from the equilibrium. We always measure from equilibrium to here. You see what I'm saying? So in this case, that would be the total energy at this position. Now the total energy, let's say at this position, say right here, and let's say it's moving this way as well. Again, we're going to get something similar to this expression. Now, which one has more total energy, here or here? They're the same. Energy is conserved, remember? So energy is always the same. So other energy in this position, this arbitrary position, or this arbitrary position is exactly equal to E, whatever that value is. Okay. Also, the energy at extreme positions, x equal A or negative A or x equals 0, is also equal to E, the same thing, because energy is conserved. In other words, so with all these equations that I have gotten, this one, and this one, and this one, and this one, I can say that at any arbitrary position, the total energy at any arbitrary position is 1/2 mv squared plus 1/2 kx squared. At the extreme right, this energy is also equal to 1/2 ka squared. Remember, at A here, the object stops, so therefore there's no kinetic. It's all potential. And at the other extreme is also the same thing, 1/2 ka squared. And so this is at x equals A. And it's also equal to 1/2 mv max squared, where at equilibrium. Right here, as I explained just a minute ago. So all these equations are equivalent to each other because energy is conserved. Okay? All right. So if I am interested, one more thing. If I am interested, let's say, again, go back to this arbitrary position right here. Or let's say I'm asked to find the velocity. Let's say I'm interested in finding the velocity right at this arbitrary position with that particular x, say whatever the value gives you. Okay, how do I do that? Well, this equation right here is any describe any arbitrary position. So all I need is just to solve for v. So if I take this equation right here, okay, write it down. 1/2 mv squared plus 1/2 kx squared equals 1/2 ka squared. I can simply solve for v. Okay? To do that, let's do the algebra. So I have to cancel out there. And if I work it out, I end up with, let's see, ka squared minus kx squared equals mv squared. You can do it your own way. So in this case, take k as a common factor. I have a squared minus x squared equals mv squared. And then solving for v squared, let's say. So that's k over m a squared minus x squared. And therefore, v is equal to the square root of, big square root, of k over m a squared minus x squared, right? And there we go. This is the velocity of the oscillating mass at any position, any arbitrary position. Basically, give me that value of x that you want me to measure the velocity of, and hopefully I know what the amplitude, the maximum displacement is, and of course I have information about the mass of the oscillating mass, and the stiffness constant of that spring. I can find you the velocity. Got it? Okay. So with this in mind, we're gonna look at a very good example in the book, example 11.5. Let's go back to the book. 11.5, page 334. Right here. That one? Yeah. Okay. Let's read it first. It has lots of questions there. It says, let's begin with a straightforward example of SHM. Again, SHM means simple harmonic motion, periodic motion, oscillatory motion, and so on. It says a spring is mounted horizontally. Here it is. So you have an air track, and you have a spring. Think of it like a fixed point, and then one end of the spring is fixed. And then this is a balance where it measures the force, you know what I mean? A classic balance. He says a spring is mounted horizontally on an air track with the left end held stationary, right there, we attach a spring balance to the free end of the spring, pull toward the right, see that? And measure the elongation. Elongation means displacement, right? We determine that the stretching force is proportional, excuse me, it's proportional to the displacement, okay? You know, F equals kx, that is. And that a force of 6 Newton causes a displacement elongation of 0.03 meter, okay? Now, why did he give us this information? You can pause the video and think about it. But here is the answer. He gives you this information to allow you to find the value of K, the stiffness constant. All right. Now, we remove the spring balance and attach a 0.5 kilogram object to the end, right there, the glider. All right. Pull it a distance of 0.04, release it, and watch it oscillate, you know, back and forth. The question is, find the following quantities. The force constant, you know, the stiffness constant, the maximum and minimum velocities, maximum and minimum accelerations, the velocity and acceleration when the object has moved halfway to the center from its initial position, and the kinetic energy, potential, and total energy in the halfway position. Okay? Not bad, really. Let's see how we do this problem. I'm trying to, if I can keep the drawing there, you can look at it. Example 11.5. So what's given to us? He said that the force is proportional to the displacement, to the elongation. Remember there was a sentence there. And he said for a force of 6 Newton, I'm reading this information from my hard copy right beside me, we get x equals 0.03 meters. Okay, this is given to us. Okay, this is given. And then he said we remove the spring balance, replace it with 0.5 kilogram object, and then pull a distance or displacement 0.04 meters, and then release and watch it oscillate in SHM. That's what he says. Now, first question, he said, what is the value of K? The stiffness constant. Well, we know that F equals Kx, and the reason he gives me those two information, x equals, excuse me, F equals 6 Newton and the displacement at 0.03, so I can just solve for K. So K in this case is equal to F over X. We plug in the numbers, so we have here F is equal to 6 over 0.03, and then we calculate that. I hope you're working with me. So I have here 6 divided by 0.03, answer 200. So here we have the stiffness constant is 200 Newton per meter. I'll write it down here and box it. There we go. Okay. That's the first part. The second part, he says, find the maximum. Okay. He said, here, let me go back. The maximum and minimum velocities obtained by the vibrating object. Vibrating, that's another word for it. So he wants V max and V min. Okay. Now these are they can be a little misleading in terms of V max and V min. If you think about it in terms of vectors, the most negative velocity is min and the most positive velocity is max. That would be one way to see it. Another way of seeing it is, well, when when velocity is 0, that will be min. It's just not moving, instead of saying. So that will be the That'll be minimum. And the maximum, of course, is when it reaches the maximum speed. Okay. All right. So where the Vmax occur? When does it occur? Well, when the kinetic energy is maximum and the potential is 0. You remember? Now where does that occur? Occur at x equals 0. Go back to where I talked about it. Here, let me go back very quickly. Right here. Right there. Remember? This is Vmax. So Vmax where? When the potential is 0, kinetic is basically a max. This is the kinetic is a max here. Okay? So basically at x equals 0, this is where the max is. Remember, it's 0 right here. Remember, it stops before it rebounds. So here the velocity is minimum. So basically the minimum is right here. Okay? All right. So it occurs at x equals 0. Maybe occurred, right? At x equals 0. And in this case, we will have k equals to 1/2 Vmax squared. And then we said that, let me go back to that formula again. We said that the Vmax, right here, see that? See this formula right here? Vmax is equal to 1/2 Ka squared. That's the maximum displacement. Did he give us the maximum displacement? Yes, he does. He did. Look, let's read the problem again. He says, we determine the stress here. We remove the spring balance and attach it to a 1/2 kilogram object, and we pull it a distance 0.04. There it is. And then what? And then let go. Release it. That means the maximum distance, the maximum stretch of the spring is 0.04. Do you see what I'm saying? So in this case, the Vmax must equal, or excuse me, the maximum kinetic energy must equal to the maximum potential, which is right here at 0.04. So I can equate that, go back. I can equate this to 1/2 Ka squared, just like I did here in this boxed equation right there, right here. So I can equate it with this Vmax, or I can equate it with that. They're all equal. So I'm going to make those two equal to find Vmax. You get the trick? And so with that in mind, let me just move to the left here. So in this case, the halves cancel out. So the Vmax is basically equal to K over M A squared under the root. All I need to do is just plug in the numbers there. So I have here K, I just found it from part A, is right there. So that will be 200 over the mass, he said is 0.5 kilogram, times A squared, he said is 0.04, quantity squared, all of that under the root. And then when I do the calculations here, I got 0.8 meters per second. That's Vmax. Make sense? This is where at equals 0, at x equals 0. Okay? Now, where is Vmin? Well, logically, I mean, if you're just looking at this picture, the one I showed you here, this picture, where is the minimum velocity? Well, the minimum velocity is basically when it doesn't have velocity. Make sense? When the speed is 0. Well, the speed is 0 is at the extreme, either here or here. Remember, it stops. It moves all the way here and then stops and then rebounds. And of course, it moves all the way to the left here and then it stops and then rebounds. So the max, the minimum velocity here. You see what I'm saying? So the minimum velocity simply is 0 at extreme point or at max displacement. Displacement. which are minus plus or minus a, that is, right? The extreme right and the extreme left. Got it? Okay. The second part, or the third part, he says the maximum and minimum acceleration. Remember I told you about acceleration is not constant in this, so it basically changes all the time. We said that. How do I find the acceleration? I just showed it to you. F equals ma, and that's equal to kx. Again, I'm ignoring the minus sign for now. So in this case, a is equal to k over mx. There it is. Okay? So if I take the magnitude of that, so a max, the maximum acceleration, well, a max basically occurs at maximum displacement. What's the maximum displacement? It's capital A, the amplitude. In other words, it's k over m a. Make sense? Just plug it in. So I have here 200 over 0.5 times the maximum displacement. He said is 0.04 meters, right? And then when I calculate that, that'll be 0.4, 200 divided by 0.5 times 0.04. Answer, I got 16 meters per second squared. Okay? Now, what is the minimum displacement? Well, one way to think about it, it's basically this is the most positive. Okay? And the minimum would be the most negative. Basically the same one, but it's on the other side, so that makes it the most negative. So just negative 16 meters per second squared. In other words, when this A is negative, for this part right here, A is equal to negative 0.04. You see what I'm saying? When it oscillates to the other side. You got that? So that will be the most negative. Okay? All right, part D. He said the velocity and acceleration when the object has moved halfway to the center of its initial position. Okay, what does that mean by halfway? Halfway, basically half the maximum displacement, half A, that is. If A here is 0.04, halfway, which is 0.02. Okay, that's the meaning of it. So halfway means A over 2, so that will be 0.02 meters. On either side, it could be positive, it could be negative. Okay? So in this case, he said, what is the velocity? Well, we go back. Remember, if you want to find the velocity at any point, you basically use this important formula that I just boxed for you. So I'm going to use this formula where x here is halfway. So I have a squared minus a over 2 quantity squared. You got that? Right here. And then you just plug in your numbers. So we have here, let me just, this formula that I just showed you is equal to k over m times a squared minus x squared under the root. I'm just going to put it to the power of 1/2 like that. And all I need to do is just plug it in. So I'll have here 200 over 0.5 times 0.04 minus 0.02. Oops, sorry, this is squared, right? And that's, sorry, squared, all the way to the half, you see what I'm saying? And then you just calculate all of that. And then when you do it, you will end up with 0.69 meters per second. He said, let me just read it again. He said, the velocity and acceleration when the object moved halfway to the center from its initial position. So in this case, it's going to be moving to the left, correct? So that's to the left. And then this case, remember, the square root of any number is plus or minus. So that would be minus here, right? Because it's moving to the left. Okay. And then he says the acceleration. Well, the acceleration is k over m. X is also moving to the left, so there should be a minus sign there, right? So in this case, we would have 200 over 0.5 times 0.02, which is a over 2, and that will give me negative 8 meters per second squared. Okay? Second squared. Did I put yeah, oops, I forgot the minimum should be negative 16 right here. Negative 16 meter per second squared. Okay, not second, per second, right? Okay. And there we go. And then the last part of the problem, he says kinetic energy, potential energy, and total energy in the halfway position. That should be easy, right? So basically the kinetic energy is 1/2 mv squared. I already got the v right here. See what I'm saying? And all I need is just plug it in. So I just have 1/2 0.5 0.69 squared, and then when you work it out, you'll end up with 0.12 joule. The potential energy for halfway is just 1/2 kx squared, so that will be half k is 200 times the half is 0.02 squared, and then you work it out, you end up with 0.04 joule. And then of course the total energy, well, what's the total energy? Well, the total energy is just k plus u, right, is equal to 0.12 plus 0.04, and when you work it out, it's going to be what? 0.16 joule. Or you can also, another way, or, big or here, remember, E is equal to what again? Here it is right here. Let me go back to that big boxed equation right there. Oops, one more. Right here. So total energy is kinetic plus potential, or I can use this one, or I can use this one, whichever. I'm going to use this one. We should get the same answer. So let's see if we get the same answer. So, or half k a squared, plug it in, half times 200 times a is 0.04 squared, and then you can work it out, and I bet you're going to get the same answer. 40. So either or. Got it? Okay, good. The next topic, which I think the last one before we end this lecture, and that is frequency period of an object in SHM. The next topic is section 11.4. And the title is Equations of SHM, Simple Harmonic Motion. Before I talk about this section, I promised you to explain what is meant by simple harmonic. Why the word simple? Okay, simple has several meanings. Remember we said periodic motion can be described by, or the restoring force that is causing the harmonic motion is a force equal to kx minus kx, right? Where x is here is the displacement, and the force is the restoring force, right? And both of them are vectors. The minus sign indicates that the displacement and the force vectors are opposing to one another, correct? All right. Because x here is a linear function, in other words, f is not equal to, say, kx squared or x cubed or 1 over x or whatever. It's basically, it's a function of the linear displacement x, okay? And in that sense, we call it simple, okay? Harmonic means oscillatory, vibratory, or periodic, okay? So the x here, because it's a linear function, so in that sense, we call it simple. Another one is, the reason we call it simple is because those kind of motions can be described by trigonometric function sine and cosine. Okay, so the word simple here, it means the motion can be described by a sinusoidal function. When we say sinusoidal, it means sine or cosine. Okay? That's really the meaning of that, the word simple. Simple harmonic motion, it means it can be described by that. All right. So, the motion of an oscillatory system can be described in the following way. The displacement of it, which is a function of time, is equal to A cosine omega t. Okay? Now you may ask, where does this come from? Now that's advanced physics. You have to come up with what is called the equation of motion, which is a second order differential equation that you have to solve. But here, I'm just giving you the simple version of it. So A cosine omega t is the displacement of that oscillating object. Okay, where omega here is, of course, is the angular frequency and A is the amplitude. Okay. The velocity is simply, for those of you who know calculus, is basically you take the derivative of the displacement. You're not required to learn that in this course, but basically if you take the derivative of that, you will get the velocity, and in this case it's going to be equal to minus A omega sine omega t. Okay, and then the acceleration is the derivative of the velocity, and that's acceleration A of t is equal to minus A omega squared times cosine omega t. So these are the equations that describe the motion of an oscillating system. Okay? One more thing. So what is omega here? We said it is the angular frequency, the one we just talked about earlier, and that's equal to 2 pi f. I'm going to write them down for you here. So I can basically write these as x of t to be equal to A cosine 2 pi f t, see that? And V of t is equal to minus A omega sine 2 pi f t. And sorry, maybe I should put it, take also this omega and replace it with 2 pi f. So that's going to be minus 2 pi f a sine 2 pi f t. You see what I'm saying? And then the acceleration A of t is equal to it's A omega squared, and so that will be minus A 2 pi f quantity squared cosine 2 pi f t. I'll just leave it like that. Okay, so that will be another way of writing it. Another thing is, remember I don't know if you remember that or not from your previous math classes, if you have let me go back to this equation right here. Just take the simple one right here. This one here. So we said that x of t is equal to A cosine omega t. So we said that this is the amplitude, which means what? The amplitude would basically the maximum displacement. In other words, this is the displacement function, x of t. It tells you basically what is the position of the particle at any time t is given by that, okay? And this is the maximum displacement that reached by the object, by the oscillating object. Now, for velocity, bear with me, v of t is what, here it is right there, minus a omega sine omega t, let me write it down, minus a omega sine omega t, okay? Well, what is that? Well, this is also the amplitude. Amplitude. Which is, here it represents, this is a velocity function, this represents the maximum velocity. See what I'm saying? So the maximum velocity, V max, is basically A omega. Okay? So this is here, A max, or excuse me, X max, if you will, is A, and V max is A omega. Well, what is the maximum acceleration? I go back to my acceleration function. A of t, we said, is equal to minus omega squared A cosine omega t, and the maximum acceleration is really just A omega squared. Is this one right here. You got it? Okay. One more thing. We said that omega is 2 pi f. I already mentioned that. Another one, again, it stems from calculus and advanced physics, but you just need to accept it. Omega is also equal to the square root of k over m. Please write it down. Write all these formulas down in one sheet. There's a lot of formulas in this chapter. They're very simple formulas, but you just need to write them down and to know how to use them. So omega, there is another way of calculating omega if you don't have the frequency. It's basically the square root of the stiffness constant divided by the oscillating mass. You got that? Square root of k over m. Now, since f is equal here, since omega is equal to 2 pi f, so that means f is equal to omega over 2 pi, so I can write it this way, 1 over 2 pi square root of k over m. See that? That's for the frequency. I'm using this formula right here to put it in there for omega. You see what I'm saying? So that's another formula. And we know that the period is 1 over f, right, in the beginning of the lecture. So I can write down tau to be equal to what? Basically the reciprocal of all of that. Basically all I need is just to reverse them, take the reciprocal of it, and it becomes 1 over 2 pi becomes a 2 pi, and the square root of k over m becomes square root of m over k. And there we go. I have an expression for the period. Okay? What else? I want to make sure I've written all the formula that we need before we do a couple of problems. I think this is it. All right. So let's go to example. This stuff is not hard, except it just has a lot of formulas. Let me do example 11.6. And that's on page 340. Right here. He says, let's go back to the oscillating air track glider, I believe the one we just did. As in that example, the force constant is 200. We got that, remember? And the glider's mass is 0.5 kilogram. Now let's find the angular frequency, he wants omega, frequency, f, and period, tau, of the glider's motion. Okay, simple substitution as you can see here. So let's see how we do that. With those formulas that you're looking at right now in mind or in your sheet. (11.6). So let's write down what's given to us first. He says the stiffness constant is 200 Newton per meter. The mass is 1/2 kilogram, and he wants the omega. Okay, we know that omega is what? Square root of k over m. Is that right? Just plug it in. It's really that simple. So it becomes 200 over 0.5, and that gives me square root of 400, right? And that will be 20 radians per second. Okay. Now he also asking for the frequency f. We know that omega is equal to 2 pi f. So f in this case is omega over 2 pi. I hear my cat is meowing. She wants to get in. We're back. So we know omega is 20, so all I need to do is just plug in. So we have 20 over 6.28, correct? And then when we plug it in, we'll get the frequency equal to 3.2 hertz, right? And then he wants the period, tau, 1 over f, correct? Just take the period, the reciprocal, excuse me. So that's 1 over 3.2, and when we do that, I will get 0.31 second. Remember, the period is just time. So tau is equal to 0.31 second. It's really simple stuff, I hope. Got it? Okay. One more topic within within this last topic, and then I'll maybe do a couple of problems from the book, from the homework. And that is the simple pendulum. Here is this word simple again, okay? And the word simple here for a pendulum is because we are assuming the mass of the bob of the pendulum doesn't change, and the string that is holding the mass is rigid. In other words, it's not elastic, okay? So it becomes a simple pendulum. Okay, so what is the simple pendulum? You know, like a grandfather clock, that's a simple pendulum. It looks something like that. Here is the ceiling. Here is the pendulum. Here is the bob, which is the mass. It's called the bob. At least in America, we call it the bob. And it is oscillating to and fro like that. Oops, I'm trying to make it an arc of a circle. Get out of here. Something like that. Okay, and so this is the vertical right here, if I can make it vertical. Right there. And this is the angle theta. It's not terribly important for our chapter. This is the length of the pendulum, L. This is the mass. And of course, it's oscillating to and fro, okay? So when you ask the question, how long it takes the bob to complete one swing, to complete one cycle. In other words, let's say you hold, the ideal pendulum, really, the one that all of us are familiar with, is the swing in a children's playground. Okay, that's basically a pendulum. So you have a child sitting on the swing. That's the bob, right? And then you get the cable is basically the string of length L, and then the child is swinging to and fro like that. Okay, that's basically a pendulum. Not as exactly a simple pendulum, but it does approximate a simple pendulum in that sense. Now, let's say you hold the child and you pull the child towards you and then let go, okay? Now, the time it takes the child to come back to you, that would be the time it takes is the period of the pendulum, okay? So it's the same thing. It's, you know, so the period of the pendulum here, tau, again, which requires calculus and advanced physics, it's equal to 2 pi square root of L over G. where L is the length of the pendulum, G, of course, is the acceleration due to gravity, 9.8, okay? Notice that the period here does not depend on the mass. This is very, actually amazing, really. It does not depend on the mass. In other words, if I have a child of, say, 3-year-old, 35 pounds or so, and I pull the child towards me and let go, and I calculate how long it takes the child to come back to me, and then I replace the child with his uncle, who is 200 pounds, and I pull the uncle the same amount and let go, I will get exactly the same period. Can you believe that? In other words, it's independent of the mass. The swing will swing at the same period regardless of the mass of the bob. Okay, that's interesting. And the evidence for that is this formula. Look at that. If the mass is important, the M would have been here somewhere, but it's not. The only thing that counts is really the length of the pendulum. The shorter the length, the shorter the period. That's it. Other than that, it does not affect it. Okay, that's the remarkable thing about this formula. It's a very interesting formula. It's independent of the mass of the bob. Okay. And then, of course, we know that the frequency, which is 1 over tau, so if I want to know how many cycles per second the pendulum is oscillating, all I need to do is just take the reciprocal, 1 over tau, which is the reciprocal of this thing, and it becomes 1 over 2 pi square root of G over L. See what I'm saying? That would be the frequency. Anything else? Okay. That's about it. So there are 2 examples in the book. Let me do them both. The one is easy. The other one is also easy. One of them is super easy. The other one is just easy. Okay. Example 11.8 and 11.9. Let me do both of them. 11.8 and 11.9. Page 342. There we go. We're basically done with the chapter. These are the last topics. Then I'll hopefully I'll have time to do a couple of problems from the homework. Okay, example 11.8 right here. It says find the period and frequency of a precisely made simple pendulum that is 1 meter long. An accurate measurement of the acceleration of gravity at the specific location. Blah, blah, blah. Okay, so it's basically that. So let's assume that G value is 9.801. Okay, and then what is the period of it? Simple. You just plug it in. Do I need to do that? It's really simple. So you just go T equals 2 pi L over G. Right there's the formula right there. Not here. What is it? Here's the formula right here. The period is equal to 2 pi L over G. So the length, he said, is 1 meter, and G is 9.80 something, 01 or something. Plug it in, use the calculator, you're done with it. It's really that simple. And there we go. So you just plug it in, 1 divided by 9.801, and then that will give you that the period of the pendulum is 2.007 seconds. And then he said, what is the frequency? Well, it's just a reciprocal of the period. So you take that, 1 over 2.007, and you get this number, and you're done, basically, okay? I don't think I need to do that. Now, let's do the second one. The second one is more interesting. The lost astronaut, okay? It's kind of a cool problem. Again, it's not very difficult at all. Okay, in this example, we will use pendulum motion to actually measure the acceleration of gravity on a different planet. An astronaut on the surface of Mars measures the frequency of oscillation of a simple pendulum consisting of a ball on the end of a string. He finds that the pendulum oscillates with a period of 1.5 seconds. Okay, that's it. He gives us the period. But the acceleration due to gravity on Mars is less than that of Earth. All right, so the G on Mars is 0.38 times G on Earth, which basically times 9.8. Later, during a journey to another planet, the astronaut finds that his simple pendulum oscillates with a period of 0.92 seconds. What planet is he now on? You see what I'm saying? All right, let's write down the story. Example 11.9. And what's given to us, he says, on Mars, let's just write down on Mars. So what does he do on Mars? Well, first of all, he said the gravity acceleration due to gravity on Mars, I'm going to call it G sub m, is 0.38 G for Earth, okay? So 38% of the gravity on Earth. And then he said that the period of the pendulum, of his pendulum, on Mars is 1.5 seconds. This is given to us, okay? Now, this is all on Mars. Now, on another planet, on other planet, he said, you have a ball oscillates, and the period of the pendulum on the other planet, so we call it X, let's call it X. On the other planet, X, is 0.92 second. And he's asking what planet is he on? All right, we want to identify it. Well, how do I identify it? I'm just going to solve for the value of G and then maybe look up the acceleration due to gravity of various planets on the solar system, I hope, to identify that planet. You got that? Do you see a plan? Okay, so let's go back to Mars first. What kind of information I can benefit from it? Well, I mean, he's using the same pendulum, so I need to know the length of the pendulum. Make sense? So here we have the period on Mars, I'll just call it M, how about that, is equal to 2 pi square root of L over G on Mars. And I got everything. So let me do the algebra and solve for L. So L in this case, if I do the algebra, square both sides, and then solve for L. In this case, L will be equal to G on Mars times tau squared on Mars divided by 4 pi, right? There we go. I got the length of the pendulum. Plug it in. He said G on Mars is 0.38 that of Earth. So that's times 9.8, correct? The period on Mars, he said, is 1.5 squared, right? Given to us. Divided by 4 times 3.14 quantity squared. I need to calculate all of that, so I'm going to use my calculator to get this. I hope you're working with me. Equals 9.8, 1.5 squared. Answer. I got 0.21 meters. That's the length of the pendulum. Now he takes the same pendulum, goes to that X planet, the one we don't know which one, which. And we want to find what planet. Well, he gives us the period on that planet for that particular pendulum, for this pendulum, same pendulum. So all I need in this case, I'm going to solve for G. You got that? So here I have the period on that unknown planet. It is 2 pi square root of L over G on that planet, X. And I need to do is to solve for G sub X. Square both sides. And therefore, G sub X is equal to 4 pi squared L over tau X squared. And I got everything. I just need to plug it in. So let me go here. So G sub X is equal to 4 times 3.14 squared times the length, which is 0.21. I just got it right here, guys, right? Divided by tau squared. I got the tau to be, he tells us what tau is. It's 0.92. So divided by 0.92 squared, and then I just calculate that, right? So I have 0.21 divided by 0.92 squared equals to 9.8 meter per second. So what is that planet? On Earth. So he's on Earth. The astronaut didn't know that. Got it? Simple? Okay. I'm going to do problem number, there are 3 problems in the homework that are where you have a graph shown and you are supposed to get information from the graph to solve the problem. So I haven't covered graphs yet. Remember I told you about the equation of motion is described by a sinusoidal function, sine and cosine. Well, what if I have that graph, a sine function or cosine function? How do you extract information? It's not difficult, but if you're familiar with basic trigonometry, you should be able to do it without any problem. So I'm going to show you how to do that. Again, number 24, number 33, and number 47, all of them depend on graphs. I'll do maybe a couple of them. Let me do the easiest one first, which is number 24. And that's on page 349. There we go. See, that is this one is also homework. Again, this stuff is not difficult at all. Don't panic. I'll show you how to do it. So here we have in 24, it said the graph shown right here closely approximate the displacement x. Here is x. Just be very careful. It's written in the wrong unit. See, this is x in millimeters, should be in meters. And then the time is in millisecond, it should be in second. Okay, so you want to be very careful about your units. See, also this graph here, centimeter and second. So again, you want to convert. Anyway, so he says the graph shown closely approximate the distance x of a tuning fork as a function of time as it is playing a single note. Okay, what are the amplitude, period, frequency, and omega, angular frequency, of the fork motion? In other words, how do you find all that from the graph? How do you extract this information? Piece of cake. I'll show you how to do it. Unfortunately, a book doesn't show you how to do that. Isn't that funny? He talks about those. He doesn't talk about those graphs at all. He just brings them in the end of the book, but he doesn't talk about them. All right. So let's start number 24. Always the first thing you need to do, graph it. Okay. I mean, you know, graph it on with your own hand, so you kind of get how it looks like. So let me graph it for you. So I hope maybe you open this page on the side, because I have it in my hard copy, so it's kind of hard to switch or toggle between them. So if I'm looking at it in the hard copy, it looks something like that. Again, when you graph, it doesn't have to be terribly accurate. Just make a rough sketch of how the graph looks like. It really helps you. So it starts from here. Let's make it start from here. And it drops down like that. Just like that. Again, this one is a cosine function. And so on. Okay, it goes on and on. I want to remind myself that this is the t-axis in millisecond. And this is the x-axis displacement in millimeter. All right? Okay. So you need to know the amplitude, or the highest point to the amplitude. Here it says 0.4. Okay? And right here is a 1. Right here is a 2. Right here is a 3, and so on. Got it? Okay. And then the lowest point, of course, is going to be negative 0.4. Okay? Here's how you do it. Remember, the x-axis here, or the horizontal axis, is time. What is the period? The period, the time it takes to complete one cycle, correct? Well, let's begin here. Okay? Imagine the object is moving. Well, where is the one cycle starting from here? Again, from your basic knowledge of trigonometry, one cycle is right until it gets here. In other words, the length of this cycle, the length of this distance is basically the period. Just the length of one cycle. You can also pick it from here to here. You know, from trough to trough rather than peak to peak if you want. Same thing, you're going to get the same answer, or this one, from here to here. That's another cycle. You can also go crazy. You can go from here to here. See that? It really doesn't matter where. That's also one cycle, whatever, okay? So all you need, since it's calibrated already, and it's calibrated in time, all you need to do is just to get that time period from here to here, or you can get the same answer, really. So let's see. The starting from 0, this is 0 right here, I hope. Let me go back to the original. Yeah, 0 to, I'm starting from here. So peak to peak, or trough to trough. Or let's say from this point to this point, and so on. You know, one cycle. So let's say from peak to peak. So I'm starting from here. So that'll be 0 seconds, excuse me, all the way to this peak, which is 2. So from 0 to 2, so basically 2 milliseconds. That's the period. You can go from peak to peak here, from 2 milli to 4 milli. Well, 4 minus 2 is 2 milliseconds, same thing. Or you can start from trough to trough, from 3 to 5. So 5 minus 3, 2 milliseconds, and so on. You got that? Simple. So here the period is, let's say, from, excuse me, you can also go from here all the way to here, if you will. But anyway, okay, let's say from peak to peak. So let's start from there, from the 0 right here to here. So that's going to be from 0 to 2 milliseconds. So therefore, the period is equal to 2 milliseconds, or 2 times 10 to the negative 3 seconds. There we go. That's the period. Now he said, what's the frequency? Well, frequency is the reciprocal of a period. So just 1 over 2 times 10 to the negative 3. Just work it out, and you'll end up getting 500 hertz. See how easy it is? Okay. Now he says omega, angular frequency. Well, just 2 pi f. So 2 pi times 500. And then you just calculate that. You'll get 3140 radians per second. Simple? Okay, what else he's asking for? He says find period. Oh, amplitude. Well, the amplitude is just the maximum displacement. Again, from your trig, it's basically the height of the wave. Any height, this one, or this one, or this one. Or the height of the trough, whatever. See what I'm saying? So this height is obviously 0.4. So the amplitude here, A, is 0.4 what? Millimeter. What's your units? So basically 0.4 times 10 to the negative 3 meter, if you will. See what I'm saying? And that's about it. Okay. Let's do another one. You know what? I'm going to have you do number 33. It's not very difficult. So I'm going to jump to 46. Right here. There's another one here. I didn't assign, did I? 39. I don't think I assigned it. Anyway, 46. He says, in the laboratory, a student studies a pendulum by graphing the angle theta that the string makes with the vertical as a function of time. Okay. Obtaining the graph shown in the figure right here. He gets this graph right here. We'll come back to it in a sec. Let me read it first. What are the period, frequency, angular frequency, and amplitude of the pendulum's motion? How long is the pendulum? He wants L here. Is it possible to determine the mass of the bob? Okay. Again, you just look at it and make a drawing of it. Let's draw it. (46), and I already have it here in front of me. Oops. And it looks something like that. My hand is shaking. There we go, something like that. Where this is the t-axis in second. This is the angular theta in degrees. All right. And let me go back to it again. Look at that. Again, always study the grid. Very, very important. So you know how it's written. Look at that. This is 1 here, right? Let me magnify it a little bit more. Look at that. So this is 1. So that means what are the calibration here? It's very important that you know that. So it gotta be 2. So that's a 2, 4, 6, 8, 10. Or sorry, it would be a 0.2, 0.4, 0.6, 0.8, 1. You see what I'm saying? This one 1.2 and so on. So make sure that you understand how the grid is written. Here, however, it's the same thing, sorry, but it's also in double. So it's starting with a 2, 4, 6, and then a -2, -4, -6, and so on. So the amplitude here basically is what? 6. 6 what? 6 degrees. Get that? 6 degrees. You can convert it to radian if you want it to radian. But the amplitude is 6 degrees, or convert it to radian. The period, well, the time to complete one cycle. Start from this point, peak to peak, from peak to peak, or trough to trough, whatever. So let's do peak to peak. Starting from here, that's 0 second, right? Remember, this is in second. So that's 0 second, all the way to what? To this number. Well, what is it? Let's see. It goes by increment of 0.2. So that's 1, 1.2, 1.4, 1.6. So that's 1.6, right? So from 0 to 1.6. So the period is what? 1.6. The frequency, the reciprocal. See what I'm saying? Omega, 2 pi f. See how easy it is? Okay. So in this case, we would have, so this one here is this, am I using the right? Yeah. Okay. So in this case, I will have the period, just by looking at it, is 1.6 second, okay? The frequency is 1 over 1.6, and if I calculate that, 0.625 hertz, right? And then omega is 2 pi f. Again, you can do that, easy. And then B. Now part B, he says what? That's part A right here. Part B, sorry. He said, how long is the pendulum? You know, the string. How long is this string? Well, we know that the period is 2 pi square root of L over G. All I need to do is to solve for L. When I do that, I'll end up getting G tau, I'm doing it in my head, 2 pi quantity squared. There we go. I already got the period right here. Just plug it in. G is 9.8. Plug all of that stuff in, and you'll give you the length of the pendulum. You do it. And then the last part, he says, here. Is it possible to determine the mass of the bob? Yes or no? Is it possible to determine the mass of the bob? And the answer is no. Why no? Because as I told you about the child in the playground and his uncle who is 200 pounds, it doesn't really matter because see, the period here does not give you any information about the mass. It's independent of the mass. That's what I'm saying. So even though if you know the period, you know the length of the pendulum, you know all of that, you know the frequency, you know the angular frequency, you know all of that, you still don't know the mass of the bob. It's independent of that. So you cannot, because it is the mass is independent of the period. Period. Okay? Okay, that's it. I think I'll stop here. If you have any question, please let me know. Goodbye.